where we will encounter if you really want to have this on our operational level, you will encounter massive problems here from the different LLMs and potential error code. But let's say we just look at it from the theoretical level and we say, this is great. Now, why I've chosen these two papers is because they reference each other. Because now this and here, particularly the reward model of Susan, is now the solution to Gears problem, the online synchronization step. Just think about it. This is now outside of the scope of both papers. This is just what I found, why I showed you this paper, why I did this video, because I think it's absolutely fascinating. If you read multiple papers, you see here potential cross-references that you can find solutions the authors were not even able to imagine. So the solution involves a repurposing here Susan's reward model in particular, but not as a tool for fusing here the pre-existing clean subgraphs, but if you want, as a more sophisticated semantic verification filter that you can apply directly after Gears online synchronization step. And I think this is nice, no? Because now the reward models with graph neural network-based encoder and query to subgraph cross attention, it's not just evaluating here the linking tribble in isolation. No, it has now the complete, if you want, absolute environment information, the context information. So it would now holistically analyze here the entire reasoning path that follows from that link. So we have more information about this, and this is here the beauty. But of course, be prepared to build this reward model, and train this reward model, integrate this reward model here from two research papers might not be the simplest.
I mean, I'd like to personally establish the Gears system, just like some regression model that takes T sub q and T prime sub q and takes these triples, the dynamic categorization, and compares. Right. But I think I have a better idea for, what do they call it there? The reward model, the GNN encoder. And I think there's many ways to get to the truth. There's just some paths that are going to take you longer and are going to be more computationally expensive. It turns out to be an energy issue. You know, how much time do you have? How much energy can you use to figure this out? I think we can figure out anything, but we are bound. We are physically bound observers, and it's like we are metabolically limited. So we have to find an algorithm, a shortcut, or a way to this path that has like a kind of like a Bayesian GNN system. Maybe like a democratically upvoted or downvoted system that then feeds back into the original data set. Or feeds back to some point. I'm not sure where. I want to figure this out though. Because like, let's say this. Let's say you wanted to explore how people thought and the types of people. So you want to kind of encapsulate everything, every which way that people can think. So how do you do that? Well, you have this system. Maybe you propose, let's say you have an app and you propose some linking through this node system. And then you ask the people democratically to vote it. Is this true? Upvote? Is this false? Downvote? Is this neutral? No opinion? You know, neutral point. Neutral vote. And then you kind of like correct it and lead it to the answer. You're creating this funnel from the widest point of the funnel being you're trying to encapsulate everything to the narrow point of the funnel, which will lead you to the node of more correctness. kind of like a ranking system, but it's a dynamically self-repairing system, or self-correcting system, I should say. You have to kind of like offload as much onto time as possible with an algorithm. Time being the deciding factor of how the correctness happens, how much correctness happens. The more time you let pass, the more correct it'll be. So you just kind of you use all these tendrils into an arbitrary, well, maybe not arbitrary, these tendrils into potential space. You put it out there, see what sticks, what doesn't, and then correct. Have a self-correcting system, which again I think a democratic system with human voting is a good way for that problem. For data sets, I think it's pretty easy actually. To have like a model that, okay, to not a model. Well, I guess it is a model. To have a model that just absorbs the data that you're feeding it, and then you can query against it. You can ask it questions through an LLM. That's pretty easy. And you can fix the scale thing by pretty much redoing it based off of the new data that you have. So you kind of have to do this, right? You let it grow the data, then you kind of like refactor. I don't think that's the right word, but then you let it grow again. So you have like these checkpoints that you're going through time, and eventually, well, not eventually. I mean, even off of the first contraction there, you would be very accurate. But the issue is that as your knowledge base grows, things get a lot more complicated. So, and your accuracy degrades. So you reindex. That's what I was looking for. So you keep reindexing at certain points in scale, because it's kind of computationally expensive as well to have a constantly indexing system, and I don't think it leads you anywhere. You kind of have to let it grow in this potential space and then reindex at certain intervals. Apply whatever algorithm, whether it's the, what is that, Louvain, the lead-in algorithm. There has to be some way to do it. So I do want to play around with this. But I was trying to do the math here. It's very hand wavy. I'll show you. Can you see that? It's kind of just a chart. Or I'm drawing what it would look like to do this. And I'm reading all these papers to see, what makes the most sense. I was looking at that Louvain algorithm because it has, where is it? Has these two sigma functions that pretty much do something very interesting. So the first sigma function represents the sum of weights of links inside the community I. It calculates the total weight of all edges that connect nodes within the same community. This measures the internal connectivity or cohesion within a community. And I agree with this, because in order to have some accuracy, you have to have more interconnectedness. I mean, just think of brains, and think of how you might have done something in the past that was unrelated to another subject that you were also working on, and in the end you realized that they were the same kind of problem. Like, well, I don't want to get too specific. For me personally, I got into cars and tuning cars, and then I got into physics and physics equations and linear algebra and calculus and solving differential equations and learning as much as I could about quantum mechanics. Solving the Schrodinger equation, things like that, and philosophy. And it turns out, I mean, the more time I let pass, the more I realized that these were all the same kind of problem. When I got good at a specific part of any one of those things, it helped me tremendously at other parts of it, because it all seems to be, a physics problem or information problem, an entropic problem. Okay, so the second sigma function, which is, so this one was I to 1. And then, so the second sigma function represents a sum of weights of links incident to nodes in community 1. This includes both internal edges within the community and external edges connecting to other communities. So you're strengthening the initial community, and then you're trying to strengthen the community to community connection. Their role in modularity calculation. These sigma functions are used in the modularity formula. Q is equal to 1 over 2m sigma of product sigma sub n minus sigma, some equation, where sigma sub n measures actual internal connections, and the other fancier sigma represents expected internal connections under random distribution. The difference gives the modularity contribution of each community. Algorithm and process. The Louvain algorithm uses these functions to do 3 things: evaluate potential community assignments by calculating modularity gain, optimize by moving nodes between communities to maximize modularity, and aggregate communities hierarchically when no further improvement is possible. So it's a process of elimination in a distribution method, in a statistical method. The enumeration, which I mentioned, which was the sigma function, typically refers to summing over all possible node pairs. So it just compares over the sum of numbers in the community. When calculating the total modularity of the network partition, these sigma functions essentially capture the balance between actual community structure and what would be expected by chance, which is the core principle behind modularity-based community detection. I like this paper. The lead-in algorithm I like a little bit more. I think it expands upon it. Let's take a look. So it does all the same thing. It includes ij in a single sigma function. So this is what it's doing. Visually, this is what it's doing. It's pretty much establishing communities, well, establishing relevancy, and then cleaving that into communities, and then cleaving the communities into even larger overarching communities. So more granularity. This is how you would do it with Python, it looks like. Very interesting stuff.
Path forward. Okay. Yeah. Now
Hey,
the
I use
third paper, and
PyG.
you see here July 22nd, 2025, PyG. Now you might say, what is this? We know PyG, no? Yes, but this is a brand new paper. Also, yeah, under the supervision von Jure Leskovich. And they say now, hey, what is the latest that we found in the latest version? We just want to show you what we have, and we focus here for the latest update here on 3 core aspects that have been refined and expanded here. I told you we are working with heterogeneous hyperelements, no? So the real-world graphs have diverse node and edge types, and now, or at least in PyG2, we have now heterogeneous graph data types that are now working automatically. We don't have to do it manually now for some years, and this is simply nice. But the first paper, remember, it was about scaling. And now, here with PyG, we have, if you want, the code to optimize here the scaling behavior of what we can build. So if you want, if you have paper 1 and paper 2, this PyG paper is the basement, the foundation, the operational code implementation that gives us here all the new code function and the code elements that we can implement paper 1 and paper 2 that we just looked at here in this video. Plus explainability. Isn't it nice? You notice PyTorch graph neural network, absolutely centric. Yes, this is here the classical PyG. If I have here a little talk, heterogeneous graph is now what's working here. We have graph transform architectures. Yes, you know this illustration here of a GNN explainer in PyG. You're familiar with this.
So yeah, I mean, you have an input, right? Q, and it'll either spit out an answer, which, I mean, it's either going to be correct or not correct. If it is not correct, it'll recirculate that back into the initial function that uses the initial data set. If it is correct, then that's where you can apply some Bayesian reasoning, you know, either upvote it, downvote it, or neutral vote. And then you ask enough people, and you're going to start to map out the truth, map a branch in this potential space towards the more accurate answer, which is less information. It's flatter. It's more efficient. I gotta try to see how I'm gonna do that though.
We have here multimodal, multi-table data with PyTorch frame in PyG.
You gotta modify the
But of
reward
course, the
system.
most important fact is here we can build here beautiful graph RAG pipelines in PyG, in the latest version of PyG. Have a look at the study. If you're not really familiar with PyG, they give you a beautiful introduction into the complexity of this specific code implementation. A natural language query is used to retrieve the relevant contextual subgraphs from a larger knowledge graph, which are then encoded via a graph neural network, and the resulting node embeddings are used to enhance now the conventional LLM encoder-decoder workflow. And they have all the code instruments that we can do this in a very intelligent and a very elegant way in coding. If you want to see this here, the complete summary, I tried to give my best. Hopefully you agree with it. GraphRag starts here with a natural language query, which is used here to retrieve here relevant contextual subgraph from a larger knowledge graph database, Neo4j for example. This subgraph is then encoded using here graph neural network, remember message parsing and everything, and the resulting node embeddings are aggregating and projected now into the LLM's embedding space. You remember the mathematical vector space that I told you that we're going to build in a, 1024 dimensional space. And PyG supports this retrieval workflow through the extension now of its feature store and graph store abstraction.
Wait. Okay. Code using GNN and the results and the resulting node embeddings are aggregated and projected into the LLM's embedding space. PyG supports this retrieval workflow through extensions to its feature store and graph store abstractions. The interface is fully customizable and can be adapted to domain-specific retrieval strategies. Yeah, I mean, but how big is your embeddings aggregation going to get when you have when you scale up?
This is fully customizable, and we can build this with elegance. G-retrieval model, yeah, compatible with Hugging Face LLM standard for today. So this is now nice because PyG as the code, as the power that the code gives us here, we can really start to build now planetary scale knowledge graphs. So we solve here, what I had in the title of this video, the problem of scaling here our GraphRec system to millions of documents and even tens of millions of documents. There seems to be now a solution, and as you see, all companies are working on it.
I just think there's a way to have people correct it for you, to leverage humans, reverse engineering. Because what's true is kind of subjective, and it depends from person to person with the non-generalized things. Obviously, you know, the physics equations are the generalized truths out there. Everything else is pretty hard to calculate. And that, in my opinion, is more subjective. I mean, there has to be some subjectivity if the observer messes up measurement or has an influence in measurement. There has to be some subjectivity because we're finitely bound observers. I think there's something there.
This because they also have the feeling maybe this is the way forward in AI. I want to show you 3 elements that I personally found interesting. Please read all 3 papers, come back, and then you will see, or maybe you disagree with me, please leave a comment. And
yeah, like it becomes a information issue. I mean, back in the day, you really had to think about how you built things because you had a limited amount of memory registers. You know, you had to be as abstract and lightweight as possible in general. Now we have the luxury that we can, you know, sift through a trillion tensors of information. And, it doesn't take that much energy. But I mean, if you follow this to the extreme, I see a future where we have LLMs that, you know, you don't want to overload it too much or it'll create a black hole because it just takes so much energy. It does so much computation. It is so dense. Like, we will be flirting with creating a black hole at that point. So we have to find these algorithms that are as efficient as possible. And who knows, maybe quantum computing will change some of this. Although I am skeptical still. I kind of agree with what Wolfram says, that quantum computing is may not lead to anything useful or too useful. It will be useful, not too useful, because you're branching off into all these threads of time, and then one of these threads gets your answer, and then you have to corral it back and that, I mean, how are you going to confirm it's right if it takes, you know, 100 million years with a classical computer to do it? Are you going to find an algorithm that will verify the correctness of your answer? Maybe it exists. I'm not sure.
implement now what here, the latest version of PyG 2.0.
I mean, you only have so much energy.
In reference here to the two papers that we just looked at, no? Susan and Gears. So what we have is an out-of-core graph processing via a decoupled storage. And this is essential. Why? Remember, Gear operates here on two massive independent data sources. No? They're used here in the publication the find web as a document index and then a canonical huge knowledge graph from Wikidata. Now, of course, a traditional GNN library would require loading one or both of these into RAM, which is, for the completeness of Wikidata, almost impossible if you're not Google or Microsoft. So what is here the PyG solution? It builds an abstraction that allows us to define a graph store that is not a memory object, but now an API client. So simple.
And maybe this graph rag thing will move beyond that. Like, how do you, because of the hyper specialization of successful graph rags or knowledge graphs, I think it's easier just to democratize everything and have them connect each other, talk to each other as if each one is in and of itself a node, and then run these apply these algorithms on top of that. So, the knowledge will be decentralized in a way, or the application of the algorithm will be decentralized, and everybody's just focusing on what they do best. The more niche your graph rag is, and knowledge graph is, knowledge base is, the more you might be able to help the overarching cause.
Can create now a Wikidata graph store and a find web graph store classes. And when the Gears agent needed to perform here the graph expansion, as I showed you in this video, on Wikidata, the sampler makes simply an API call to the Wikidata index. And when it needs to retrieve those features, it makes a separate call. So we have an out-of-core computation as an elegant and the single most critical innovation, enabling now here the Gears architecture. So you see, we have the code elements to implement here Gear in a very nice and efficient way. But we have I have another idea that maybe we can implement this heterogeneous message passing here that is really here automatically done. Eh? Because you remember here, especially
so
here for Susan and Gear, if we would do this in a classical manual way, it is an
I agree
error.
with that. That kind of talks again to what Wolfram is saying. I'm not sure if his physics project is the right way to think about things, but there seems to be some parallels between that and this, because you're looking for that rule, that one rule that if you repeat over and over will give you, the truth that you're seeking. Because I do honestly believe if you go up, down, left, right, left, down, up enough times, you can compute anything.
Prone nightmare. I mean, at least for me. So if we work now with the two hetero function, PyTorch automatization, simple homogeneous GNN model and a schema of the graph, and it automatically generates here the complex multi-layered heterogeneous model. So nice, all done by the code. Everything is coded for you already. It really lowers here the barrier to entry. No? Make it feasible to define and train your sophisticated graph neural network here, especially for Susan's reward model, directly on a graph like Wikidata. It reduces your cost significantly. And the third point I would like to mention here, really the last element here, is batch sampling and computation on GNN. No? I told you that here Susan's reward model needs to be trained. We have to require here creating training batches, where each item is of course here a query, a candidate subgraph, and a score tuple, and the candidate subgraph is not a single item, but now a complex data structure. And in the latest PyG 2 update, we have highly optimized data and data loader objects that can now exactly do this, efficiently batch these subgraphs together. We have a more complex.
See, but with the ranking system that I'm speaking about, with using people, social engineered ranking system that then gets recirculated back into the original formula, is that if people know they might answer incorrectly and mess up everything. So they can't know. Maybe you make it a fun game. And they're secretly solving these node dilemmas on the back end.
Data structure that can handle this and everything is simply looking great. And you know what? The core of the reward model, everything we do is fast enough to make the training of millions of such query subgraph pairs practical. So we don't only have here the hardware computer infrastructure, but software
we need a good
coming
physicist.
up and able to do this. The classical, I would say...
a good philosophy major. You kind of need everything to figure this out.
Way to learn heterogeneous graph learning is here the official literature,
and a programmer,
official manual.
I
But I think I would like to stop here, have a look at the paper, get familiar with everything, because in one of the next videos we will continue to build 25. If you're not familiar, I would recommend this paper here, where they introduce you to gear. This is
they're kind of funneling it into
2025. Same Huawei technology. And gear is simply a graph-enhanced agent for retrieval augmented generation. Yeah, I'm gonna help you a little bit. So what we say is we have here our original query Q. This is the natural language question here that I asked.
I like this too because it does.
Then we simply have
the original query Q goes in base retriever, reads your information in two forms, T prime sub Q and TQ, and these would be the triples, the dynamic categorization. It does the graph expansion. What is C prime sub Q? That goes into RRF. What is that? Is that where it merges? I would assume. And then it either spits out C sub Q or it enumerates between C sub Q 1 up to N, some number. So comparing goes into a database, does something. The filter is the reward system. Is it? Filter, yeah, I mean, it's either let me see. Could be where they do global search, local search, drift search. So T prime sub Q of N goes here. Did it satisfy the question, the initial query? Q, no. If it says no, it goes back into the base retriever. If the answer is yes, it goes to the filter. G to the power of N. What is the filter? I'm pretty sure that is that. We could probably add that that human ranking system somewhere here, maybe after, or maybe that's in the filter. It's going to go somewhere here. So if it's no, it goes back, loops back around. If it's yes, it continues. And then C sub Q to the N power is the multi-step output. Wait, no, this is just to create the graph and the multi-layers. Yeah, single step process is going to be like, it's a one hop Multi-step will be n hops. Accumulate iteratively.
Base retrieve.
Nice. Original query queue is a natural language question from the user, obviously. Base retriever, so this thing here. The query first goes to a standard non-graph retriever. The paper notes that this is a hybrid of dense and sparse retrieval. So it does both. Dense and sparse is the T prime sub q and the TQ triples. Its job is to perform a first pass search over the entire document corpus C. So corpus C and the enumeration, I keep calling it enumeration, it's not that. So C sub q of 1 up to n. So it could be infinite for all we know. Well, if you have the energy in computation, if you have the metabolic energy. So passage C, the retriever returns a set of relevant text passages. That's this one. Okay, I see. That's where it attaches the passages. So it can keep the gist of it. It can keep the canonical relevance. Well, is that right? It's a description. These passages, along with the query queue, are fed into reader module. This is a small efficient LLM. Its job is to read the text and perform proximal triple extraction. So that's where it creates the dynamic categories. T prime sub q, proximal triples. This is the output of the reader, a small set of temporary, informal subject, predicate, object. Triples extracted directly from the text passage C.
Query goes to a standard non-graph retriever, and its job is simply to perform a first pass search over the entire document corpus that I have if I work, for example, in a particular domain like theoretical physics. And then extract my passages. This is the retriever returns here a set of relevant text passages. This is the result of the search if you want. And then we feed it now to a reader. Now the reader, along with the query queue, the passages and the query are fed into the reader module. I'm going to show you here the prompt for the reader module in some minute time. What is? It's another efficient little LLM. They go here, I think, with a 10 billion LLM, and the job is easy. The only job of the reader is to read the text and perform here a triple extraction, a proximal triple extraction, because we only work here on kind of a subdomain subgraph structure. And we have not one the gap between the text world and the graph world, and our triple link is now interesting. So we have both. Text, we have the proximal triplets, and this arrow here, if you want, represents the online knowledge synchronization step.
The knowledge
so
graph.
This is now interesting. So what you need now.
So triple link, where's that at? It's right here. So that's how you go into the node. That's how you enter this node network web with some intelligence, at least with some regularity. Triple link. This arrow represents the online knowledge synchronization step. Each proximal triple T prime is in T prime sub Q is used as a search query to find the most similar canonical triple T in the massive external knowledge graph. So it's looking for nearest partners, and the other one is looking for, no, these are the entry points into the graph. This is the result of triple link, a set of canonical triples from Wikidata that are now linked to our query. Oh, then it looks for canonical relations. These are entry points into the
link to the read one. From and here in the paper, they go with a class.
Graph expansion, starting from the canonical triples T sub Q. T sub Q. The system performs a search within the Wikidata graph to find new multi-hop reasoning paths, so novel finding. The paper specifies this is a diverse triple beam search. This means it doesn't just find one path, but explores multiple promising paths. Again, you're throwing out, you're casting a wide net of tendrils into potential space, trying to see what sticks, but explores multi-promising paths simultaneously to gather a wider range of evidence. C sub Q passages. Well, it's not. I forget what that little squiggly line is called. The re-retrieval. The new triples discovered during graph expansion are then used to requery the original document, corpus C. Which I guess would be somewhere here. This is a crucial step. The system uses what it learned from exploring the graph to find new documents that the initial base retrieval might have missed. So it's enriching the data.
Diverse triple beam search algorithm. So this means you don't find just one path on the hypersurface of your knowledge graph, but you explore in parallel multiple promising paths simultaneously to gather here a wider range of evidence. Great, this is it. So what you do have now, additional information. So the new triplets now discovered now during the graph expansion are simply, guess what, used to requery the original document corpus C. So this is the crucial step, The system understood that it learned now additional domain-specific information, and the system uses what it learned from exploring the graph, the Wikidata graph, to find now new documents that the initial base retrieval might have missed. So we are operating here in a beautiful loop. Now comes the next simple step.
We combine the evidence from the simple text search and the advanced graphs-based search into a unified result set, RRF, reciprocal rank fusion. Okay, so that is the fusion. We now have two sets of retrieved passages, the initial set C and the graph expanded set C sub Q. So C sub Q. Okay. The RRF box signifies that these two ranked lists of documents are fused into a single, more robust ranked list. RRF is a simple but effective technique for combining results from different search systems. All right, let's move on.
And we don't have
passages memory P of n and triple memory G of n. These boxes represent the agent's internal state or scratchpad. After each iteration, the retrieved passages and discovered triples are stored here. Stop. After one full cycle of retrieval and fusion, the agent's LLM brain makes a decision. It looks at the accumulated evidence in G of n and the query history. So it keeps the query top of mind, and then takes into account everything else. Is the question now answerable? If yes, it stops. So if yes, it stops and it continues this way. If no, it needs more information. It goes back into the loop. Q of n update query. So that's Q of n. So it would pretty much ask again, did I get this right? What am I missing? Goes back in. The rewrite step. If the decision is no, the agent rewrites the query, for example, so it requeries. For example, and it could re-requery. It could do this loop, a million times probably. For example, if the initial query was complex, the rewritten query, Q of n, might be more specific to sub-questions needed to make progress. So it's building a logic path. And it's just drilling down. This new query then becomes the input for the next cycle. That's so good. But what if this input query, so this input query can be democratically voted on as well. You can add a human element here. So for example, if the initial query was complex, the rewritten query Q of n might be more specific sub-questions needed to make progress. This new query then becomes the input for the next cycle, starting again at the base retriever. the entire process loops.
LLMs. So we have now and with the passages, because guess what?
So this turns one-shot retrieval process into an iterative agentic reasoning loop that can tackle more complex problems step by step. Beautiful.
We head back to the L7, and then run again through the process, and then I should be able to maybe find a solution immediately. Of course, you have to have filters, and guess what? Final filter step, so another LLM prompt is used here to prune any irrelevant information here from our...
So the filter, which I was curious about, once the agent decides to stop, the final collection of passages P of n and triples G of n might still contain some noise. A final filter step, another LLM prompt, is used to prune any irrelevant information. Final answer generation, the filtered evidence is passed. Maybe at the filter point we can install that social reverse engineering voting system. Large LLM which synthesizes the answer. Output type, single step output. The result after just one pass through the main retrieval loop, single step output, C sub Q. Multi-step output, the result after the agentic loop has completed multiple iterations, gone through the loops, C sub Q of n, I suppose.
A golden data set. And finally, we have an answer generation query. Dynamically bridges the gap to a massive structured knowledge base. This is Wikidata that we use. Explore that particular base to enrich its understanding, get all the context information, the context engineering, we would say, in today's speech, and iteratively refine here its search until it has gathered enough high-quality evidence to provide here a confident answer to the human. And you might say, but there's a possibility that something goes wrong. Absolutely. We have to talk about this. But in general, let's...
So query, potential entity, gets vectorized, chunking, turn into graph, embedded, vectorized, goes into a real entity. What is that? So subgraph construction, you're constructing the subgraphs. One hop relationship is nearest neighbor. Multi-hop relationship, nearest neighbors. Importance-based relations, knowledge graph. Based off of importance. Goes into a reward model for fusing. Fuse is based off of something. Oh, it's right here. So this is what it's doing with the information each step of the way. I'm guessing this is some linear regression type thing. Then it goes into fusing. Chunks it here, rearranks top chunks. Top chunks are the dynamic categories, I guess. LLM output. Or top chunks are the more relevant or the more likely data. Let's see here, knowledge graph, query. Goes into the same thing, does that, it does that, that T prime sub G and regular T sub G to find a nearest node that enters this space in the graph system. Let's see, subgraph, the fusion knowledge graph. yeah, I mean, we'll see what happens.